So in the last video, we talked about, or we did some examples with caffeine in doing calculations involving the mole, specifically converting from grams to moles using molar mass, and then going from grams to moles and moles to molecules using Avogadro's number. The fact that there are 6.02 times 10 to the 23rd of whatever you're counting in 1 mole of whatever you're counting. So to do the last two problems of that review page on caffeine, we need to say something about how we can use a chemical formula itself as a conversion factor. And before we do an example using an actual chemical formula, let's do an example using a clover leaf. Usually when I teach this, at least during the spring, this slide comes along around St. Patrick's Day, so it's very appropriate, but it'd be even more appropriate if it was a four-leaf clover, but sadly it's not. But let's say that you're picking clovers with your toddler or niece or nephew, and let's just say all of the clovers that you're picking all have 3 leaves, and let's say you pick a total of 14 clovers. And let's say for whatever reason, maybe you're doing a science project with him or her, you want to know how many total leaves you have collected in those 14 clovers. Now you could count each individual leaf, or you could use your knowledge of conversion factors and of mathematics to do a problem where you write down the number of clovers you have, use the actual clover itself as a conversion factor, saying that, oh, for every 1 clover, there are 1, 2, 3 leaves. Write that as a conversion factor so that your units cancel properly. You're left with leaves, because that's what you wanted to know, is how many leaves you collected. And then doing that appropriate mathematics, that appropriate multiplication, you get 42 leaves. So that's using a sort of a example with clovers, but you can do, as a conversion factor, you can do something similar with a chemical formula. If you have a chemical formula, like for example, calcium carbonate, I can use the subscripts in that chemical formula to relate moles of part of the molecule to moles of the entire molecule. What do I mean by that? For example, let's say I have 1.7 moles of calcium carbonate, and I want to know in that amount of calcium carbonate how many moles of oxygen I have. So I'm given moles of the total, and I want to find moles of the part. Well, the way that you can relate moles of the total to moles of the part is by using, again, moles, but those subscripts of the balanced chemical formula. Again, another example as to why writing balanced chemical formulas, that skill that you learned in Chapter 5, is so important. From this correctly written chemical formula, I can see for every 1 mole of the whole thing, I have 3 moles of oxygen. I could also say for every 1 mole of calcium carbonate, I have 1 mole of calcium and 1 mole of carbon. But in this problem, they wanted to know how many moles of oxygen. So I'm going to use those subscripts of the balanced chemical formula as a conversion factor. Again, written as a fraction and written appropriately so that my mole units, my mole of calcium carbonate cancels. I'm left with the moles in the numerator, specifically moles of oxygen. And then doing that multiplication gives me how many moles of oxygen I have. So the take-home message from this example is that you can use the subscripts of the balanced chemical formula to relate moles of the entire molecule to moles of part of the molecule. You can do that on a mole basis. You could also do it on an atom and molecule basis. So for example, for carbon dioxide, for every 1 mole of carbon dioxide, I have 2 moles of oxygen. I can also say for every 1 molecule of carbon dioxide, I have 2 oxygen atoms. Please note, you cannot say that for every 2 grams of oxygen, there's 1 gram of carbon dioxide. That is not true. That's not true because when you look at the periodic table, you see that carbon and oxygen weigh different amounts. So you cannot use the subscripts in a balanced chemical formula to relate grams, but you can use subscripts as a conversion factor to relate part of the molecule in terms of atoms or in terms of moles and the entire molecule. That's a really important point for this video and to finish problems or parts 4 and 5 of the caffeine slide. So, I'm sorry, numbers 5 and 6 for the caffeine. Sorry. So if you look at numbers 5 and number 6, I give you amounts of caffeine, the entire molecule, and I'm asking for an answer of part of the molecule, specifically of nitrogen. And number 5, I'm asking for how many atoms of nitrogen are in that many grams of caffeine. So I'm going from the entire molecule to just part of it. So now there's no way we can go from grams of caffeine to atoms of nitrogen in just one step. But you do now know from the previous slide that, hey, looking at my balanced chemical formula, my molecular formula, I know for every 1 molecule of caffeine, I have how many nitrogen atoms? Hopefully you're now shouting out to me, 4. There's 4 nitrogen atoms. So you can use that relationship to convert molecules of caffeine, which you found in number 4. You found that is, or we did that in the last video, is 1.6 times 10 to the 20. You can use that along with the relationship between 1 molecule and number of nitrogen atoms to solve for number 5. Whoops. So in number 5, sorry about that, I already gave you the answer to number 6 there. So for number 5, write down the number of molecules that you have, unit that you're looking for. And as we said in the previous video, or in the previous slide, for every 1 molecule of caffeine, there are 4 nitrogen atoms. Again, I got that 4 from the subscripts in the balanced chemical formula. I write that so my molecule units cancel. I'm left with nitrogen atoms. And so then doing that multiplication, I have 6.3 times 10 to the 20 nitrogen atoms. Last but not least, you were asked how many grams of nitrogen were in a particular amount of caffeine. Specifically, how many grams of nitrogen, which, yes, that is the answer, but let's talk through the answer. How many grams of nitrogen are in 0.050 grams of caffeine? To relate part of the molecule to the entire molecule, we use the subscripts again in terms of moles. So we have to get this 0.050 grams of caffeine into moles of caffeine. No, we can easily do that using its molar mass, which we found in the previous video, molar mass of caffeine. So now from this first step, I have an answer that's in moles of caffeine. I can convert my moles of caffeine to moles of nitrogen, again, by using those subscripts of the balanced chemical formula. And my dimensional analysis written so that my units cancel. If I was to stop the problem here, I would have an answer in moles of nitrogen, but I need grams of nitrogen. So to get from moles of nitrogen to grams of nitrogen, I need to use the molar mass of nitrogen. So from your handy dandy periodic table, you should see that for every 1 mole of nitrogen, there's 14.01 grams of nitrogen. So then written appropriately, so in your calculator, 0.050 divide by 194.22. multiply by 4, multiply by 14.01 should give you the final answer of 0.0015 grams of nitrogen. So this dance, this three-step of going from grams to moles, moles of the entire compound to moles of part of the compound, moles of part of the compound to grams of part of the compound, is one that you'll need to be able to do for your quiz and your exam. And the final slide for this little vignette is just another example that shows you a similar calculation, but in this case, you're using sodium chloride. You have an amount of sodium chloride, grams of sodium chloride, and they want to know how many grams of sodium that is. And so that dance is very similar to what you did with caffeine on the previous slide. There are several other examples on the 2 Canvas worksheets that I have posted, so I would encourage you to try those. So that is the end of this little vignette with regards to doing calculations with moles and grams and molecules. In the next video, we're going to remember those same concepts, but be able to use them when calculating mass percents, empirical formulas, and molecular formulas.